Good day, everyone. Today, our topic is about magmatism. Volcanic activity is one of the most powerful forces in nature. Although it is often a destructive force, volcanoes are amazing facets of creation. They come in a variety of shapes, sizes, and eruption types. Volcanoes erupt when magma, red-hot liquid material, seeps up through a vent in the earth. More violent eruptions occur when pyroclastic material, a mixture of magma rocks, ash, and hot gases, is exploded upward by pressure caused by underground gases and magma. When magma flows above the surface of the earth, it is called lava. Usually, lava changes from bright red to duller red, gray, or black as air causes it to cool and solidify and eventually become rock. Magma is the molten or semi-molten natural material from which our igneous rocks are formed. Magma is found beneath the surface of the earth, and evidence of magmatism has also been discovered on other terrestrial planets and some natural satellites. Viscosity of magma. Magma is molten or melted rock below the surface. Magmas can differ in their mineral content. For example, basaltic or mafic magma forms at the mid-ocean ridges or hot spots under the ocean crust and is high in iron and magnesium, but is low in silica. Silica is found in the form of little pyramid-shaped building blocks called silica tetrahedrons. Rhyolitic 7 granitic magma forms from the partial melting of continental crust and is low in iron and magnesium, but high in silica. The silica content of a magma determines whether it is viscous or fluid. Basaltic or mafic magma has a low silica content, and andesitic or intermediate magma has a medium silica content, while rhyolitic magma has a high silica content. As the silica content of a magma increases, the silica tetrahedrons tend to bond together into chains. In addition to silica, magmas will contain metals such as iron, magnesium, and calcium. Basaltic magma is associated with volcanoes such as Mauna Loa of Hawaii, which erupt frequently but are not very explosive. Andesitic or intermediate magma is associated with composite volcanoes such as Mount St. Helens or Mount Vesuvius, which are explosive but do not erupt very often. Rhyolitic or granitic magma rarely comes to the surface. When it does, it forms a supervolcano such as Yellowstone or the Long Valley caldera. Such volcanoes are so explosive that they do not usually produce a volcanic cone, just a caldera where the ground collapses after a magma chamber empties itself. Magmas can vary widely in composition, but in general, they are made up of only 8 elements. In order of importance, oxygen, silicon, aluminum, iron, calcium, sodium, magnesium, and potassium. Oxygen, the most abundant element in magma, comprises a little less than half of the total, followed by silicon at just over 1/4. The remaining elements make up the other 1/4. Magmas derived from crustal material are dominated by oxygen, silicon, aluminum, sodium, and potassium. The composition of magma depends on the rock it was formed from by melting, and the condition of that melting. Magmas derived from the mantle have higher levels of iron, magnesium, and calcium, but they are still likely to be dominated by oxygen and silicon. All magmas have varying proportions of elements such as hydrogen, carbon, and sulfur, which are converted into gases like water vapor, carbon dioxide, and hydrogen sulfide as the magma cools. Magma. There are 3 basic types of magma: basaltic, andesitic, and rhyolitic, each of which has a different mineral composition, gas content, temperature, and viscosity. Composition: basaltic magma. Gas content. At depth in the Earth, nearly all magmas contain gas dissolved in the liquid. But the gas forms a separate vapor phase when pressure is decreased as magma rises toward the surface. This is similar to carbonated beverages, which are bottled at high pressure. The high pressure keeps the gas in solution in the liquid, but when pressure is decreased, like when you open the can or bottle, the gas comes out of solution and forms a separate gas phase that you see as bubbles. Gas gives magmas their explosive character because volume of gas expands as pressure is reduced. The composition of the gases in magma are, mostly, water vapor with some carbon dioxide, minor amounts of sulfur, chlorine, and fluorine gases. The amount of gas in magma is also related to the chemical composition of the magma. Rhyolitic magmas usually have higher dissolved gas contents than basaltic magmas. Temperature of magmas. Temperature of magmas is difficult to measure due to the danger involved, but laboratory measurement and limited field observation indicate that the eruption temperature of various magmas is as follows. Basaltic magma, 1000 to 1200 degrees Celsius. Andesitic magma, 800 to 1000 degrees Celsius. Rhyolitic magma, 650 to 800 degrees Celsius. Viscosity of magmas. Viscosity is the resistance to flow opposite of fluidity. Viscosity depends primarily on the composition of the magma and temperature. Higher silica content magmas have higher viscosity than lower content magmas. Lower temperature magmas have higher viscosity than higher temperature magmas. Viscosity decreases with increasing temperature of the magma. Thus, basaltic magmas tend to be fairly fluid, low viscosity, but their viscosity is still 10,000 to 100,000 times more viscous than water. Rhyolitic magmas tend to have even higher viscosity, ranging between 1 million and 100 million times more viscous than water. Note that solids, even though they appear solid, have a viscosity, but it is very high, measured as trillion times the viscosity of water. Viscosity is an important property in determining the eruptive behavior of magmas. Magmatism. How magma forms. Earth is divided into three general layers. The core is the superheated center, the mantle is the thick, middle layer, and the crust is the top layer on which we live. Magma originates in the lower part of the Earth's crust and in the upper portion of the mantle. Most of the mantle and crust are solid, so the presence of magma is crucial to understanding the geology and morphology of the mantle. Differences in temperature, pressure, and structural formation in the mantle and crust cause magma to form in different ways. A. Decompression melting. Decompression melting involves the upward movement of Earth's mostly solid mantle. This hot material rises to an area of lower pressure through process of convection. Areas of lower pressure always have a lower melting point than areas of high pressure. This reduction in overlying pressure, or decompression, enables the mantle rock to melt and form magma. Decompression melting often occurs at divergent boundaries where tectonic plates separate. The rifting movement causes the buoyant magma below to rise and fill the space of lower pressure. The rock then cools into new crust. Decompression melting also occurs at mantle plumes, columns of hot rock that rise from Earth's high-pressure core to its lower-pressure crust. When located beneath the ocean, these plumes, also known as hot spots, push magma onto the seafloor. These volcanic mounds can grow into volcanic islands over millions of years of activity. If the raised geothermal gradient becomes higher than the initial melting temperature at any pressure, then a partial melt will form. Liquid from this partial melt can be separated from the remaining crystals because, in general, liquids have a lower density than solids. Basaltic magmas appear to originate in this way. Upwelling mantle appears to occur beneath oceanic ridges, at hot spots, and beneath continental reef valleys. Thus, generation of magma in these three environments is likely caused by decompression melting. Transfer of heat. Magma can also be created when hot, liquid rock intrudes in Earth's cold crust. As the liquid rock solidifies, it loses its heat to the surrounding crust, much like hot fudge being poured over cold ice cream. This transfer of heat is able to melt the surrounding rock, the ice cream, into magma. Transfer of heat often happens at convergent boundaries, where tectonic plates are crashing together. As the denser tectonic plate subducts or sinks below, or the less dense tectonic plate, hot rock from below can intrude into the cooler plate above. This process transfers heat and creates magma. Over millions of years, the magma in the subduction zone can create a series of active volcanoes known as a volcanic arc. See flux melting. Flux melting occurs when water or carbon dioxide are added to rock. These compounds cause the rock to melt at lower temperatures. This creates magma in place where it originally maintained a solid structure, much like heat transfer. Flux melting also occurs around subduction zones. In this case, water overlying the subducting seafloor would lower the melting temperature of the mantle, generating magma that rises to the surface. Tapping into magma's potential. In 2009, the Icelandic deep drilling project created a well that uses magma to generate geothermal energy. Normally, geothermal energy is created by pumping water into hot volcanic bedrock, creating steam that is then harnessed to generate electricity. While normal geothermal sources average around 60 degrees to 80 degrees Celsius, 140 degrees to 176 degrees Fahrenheit. The magma will steam reach a record-breaking temperature of 450 degrees Celsius or 842 degrees Fahrenheit. This huge increase in temperature allowed just one magma well to generate roughly 36 megawatts of electricity, powering 36,000 homes. In comparison, one single wind turbine generates between 1 to 3 megawatts. And that ends our lesson. Thank you for listening.